Welcome, everybody, to our first session of the Astronomy Summer Seminar Series, or the Spring Seminar Series, as we're starting a little bit early this year. I think we're all excited to get some science talks going and to share all the diverse and interesting research being done in astronomy here in Victoria. Today, we'll be having our first session with Willis, who's going to be telling us about the search for alien life. During the presentation, I don't want anyone to speak, so if you can, mute your audio, and if there's any issues, Vita and I will be able to handle any sort of noise issues. If you have questions during the talk, feel free to raise your hand. If you haven't used Blackboard before, at the very bottom of your screen, there should be a little button with a little figure raising its hand. You can scroll over it and just raise hand. Click that, and we'll come back to you at the end of the presentation to answer questions. Or if you have any issues with your connection, feel free to put it in the chat box. We're sort of test running Blackboard, so we'll see how it goes, but I think we're hoping to see something pretty smooth. You can join us next week. We'll be having a summer seminar session every Wednesday at noon. But for now, I think we'll hand over to Science and begin the presentation. So, John, take it away.
All right, thank you very much, Mallory. So my name is John Willis. Obviously, a lot of you guys know me, but it's always nice to start with an introduction. And the idea in giving this talk to you today was really to just get the ball rolling. So, though later in the session, over the summer, we're going to have probably some great science talks in a lot of detail, I set the bar exceptionally low for this talk, right? So this is just going to be a fun talk. This is actually a public talk I've given many times before, but it's some cool stuff, and I hope it's going to be of interest to you. But the idea is this is just an opportunity for us to get together, hear some science, and be a community, whether that be in person or online. So without further ado, let me start by sharing my presentation with you. So just takes me a couple of clicks to do that. So let's go here. Okay. All right. So if I press play now, hopefully you guys should all be able to see my presentation. Okay. So the title is All These Worlds Are Yours, The Scientific Search for Alien Life. And the title is really, it's just the title of a book I wrote a few years ago that grew out of my Astronomy 201 Life in the Universe course. And essentially, so that book has encapsulated a lot of my knowledge about astrobiology. It's also motivated and given me the opportunity to have additional adventures. And that's really what I wanted to talk to you guys about today. So really, I mean, without further ado, let's start off by, asking the biggest question of all. Do aliens exist? Are they really out there? And this is just a fun way of getting our preconceptions out there early in the talk, because really our preconceptions are going to be something we can't ever get rid of when we look for alien life, but we'll always try and be aware of it. Okay. Now, the biggest question of all is, are aliens out there? Well, some people are surprised at the initial way I answer this question, because the answer is emphatically yes, aliens are out there. Okay. Now, because this is an expert audience, you can hopefully appreciate the mathematics of my answer and also appreciate how unsatisfying an answer it is. Essentially, if we live, our universe, we know, is not merely big, okay, it's incredibly large. It's larger than we can actually measure because it goes beyond the observable horizon, and it's possibly infinite in size. And so you guys know, it doesn't matter how small the possibility for life existing elsewhere is, as long as it's non-zero, the chances of you getting that lucky roll, if you roll the dice an infinite number of times, are always going to be greater than zero. Okay, you're always going to have some lucky rolls and have life existing somewhere. Okay, so that's why I tell people at the start of this talk, the answer is emphatically yes. I also remind them that that's a completely unsatisfying answer, because it actually tells us nothing about what that life is, what it does, how it metabolizes, does it like the same movies as us, whatever, right? And so astrobiology asks the question in a different way. Is there any scientific evidence for life beyond Earth, right? And the answer to that question is just as emphatic, and it's no, all right? And so although we have this preconception that life may be out there, we currently lack scientific evidence to prove it. And so astrobiology, as it exists at the moment as a subject, is basically answering the question, well, how do we go out there and possibly get that evidence? And this talk is essentially going to be about two examples that illuminate that process. It's not going to be a catch-all, trying to include everything talk. I'm going to focus on just two adventures I've had that really illustrate astrobiology in action. All right. Now, one of the great things about sharing my screen this way is I can't see what the next slide is, so it's a surprise for me as well. Okay. This is great. This is the slide I show to bring us back down to earth when people think you can look for life anywhere in the universe. Okay, so here is the Hubble Ultra Deep Field. Okay, and the reason I'm showing this to you is because of that little galaxy down there in the bottom right, that quite obvious spiral galaxy that you might say is a good representation of what our galaxy might look like when viewed from the outside, which is, of course, a view we don't normally get. And so what I'm going to do then is everything I'm going to talk about, actually in my entire course of astrobiology, basically happens in that red circle. Okay, that red circle marks the limits of where we can actually search for life at the moment. And that limit, if you're interested where it comes from, that basically comes from the limit of sensitivity of the Kepler Space Observatory when it was doing its main planet finding mission that's ended now. That's basically as far away as star could be, where you would still have geometric precision to the transiting exoplanet. So that's kind of what sets the maximum limit of where we can actually search for life. And everything else I'm going to talk about is within that. And so that really reinforces the point that that argument I used in the very beginning that uses the idea of an infinite universe and life must exist somewhere is doubly unsatisfying because it doesn't represent the reality of where we can actually look. Okay, so what we're really asking the question is, can we obtain scientific evidence for alien life within that red circle? Okay, it's basically, like I said, this whole talk is about lowering expectations, down, 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 down. Okay, now we do need, though, some preconception about what to look for. We're scientists, okay? We need a template. We need to design experiments. We need to actually not just obtain evidence, but be able to recognize positive evidence when we see it, okay? So we have to put some preconceptions in there about what kind of life we're looking for. And you saw with the first slide I gave you that the preconception of alien life for some people making science fiction movies in the 1950s was 50-foot tall crab creatures. Okay, if you want that to be your preconception for alien life, that's great, go for it. Our preconception is going to be a little bit different, and this is a wonderful slide that basically shows, the life we're going to look for, but magnified on a grand scale. What you're actually looking at here is Great Prismatic Lake in Yellowstone National Park. And for scale, you can see running along the bottom there, there's kind of this wiggly grey feature. That's the boardwalk. And if you look in even closer, you can see individual people walking on that boardwalk. So that gives you the scale of the image. And then what you see here is a hot spring. So water deep underground has been heated by coming into contact with hot rocks. Hot water is more buoyant than cold water, so it rises up to the surface and it comes out in the very center at something close to about, let's say, 95 degrees Celsius, okay? Completely blue, completely clear, because nothing is living in it, and all of the minerals in there are nice and well dissolved. But as you go to the edges of the lake, the temperature drops, and then you reach the margins of the land and you see these bands of color. And those bands of color are essentially, each band of color is a different species of high temperature resistant microbes. I can't say bacteria because we have to include the archaea in there as well. So I'm always going to try and say microbes that we're looking at here. And this is our preconception as to what we think life elsewhere may look like. It's going to be basic single cellular life. Okay, we're going to recognize it via some kind of biochemical test, whether looking for some biochemical recipe unique to its own signature, its physical makeup, or some biochemical recipe that flags its metabolism, its waste product, something like that. So this is our preconception. Now also, in the absence of actually having obvious examples of life, we change our search strategy a little bit and we look for obvious examples of the ingredients for life and we use those as our starting point as the best practical places to search, right? And this is another theme that's going to come through the talk. You can't look everywhere. We just don't have enough dollars to do that because every mission costs money, right? And so you have to find a way of almost like doing a triage of passing all of the various places you might look for life, and then say, well, which are the top 3 I might actually be able to afford to go to? And the way we typically do that is based upon ingredients for life, okay? So based upon this model for single-celled life as of our template for alien life, what are we going to look for? Well, we basically reduce it to 3 components. One is water, okay? Now, the principal role of water for us and also for microbes is water is the medium in which our biochemistry occurs, okay? If you are particularly well adapted, you can actually use the water in chemical reactions as well to, or even break it apart as a source of hydrogen and oxygen. But mainly water is providing the medium in which the biochemistry is going to occur, okay? Now, biochemistry itself, right, basically, as astronomers, we're still essentially physicists at heart. So we're very reductive people. We like to reduce all kinds of processes to their most basic ideas. Well, biochemistry is basically rearranging carbon atoms, okay? And so the second element on our list is basically molecules containing carbon atoms that we as living systems can rearrange. And that process of rearranging is really what we call life, okay? And then thirdly, what makes that rearrangement happen is energy. We need to break bonds and allow them to reform, okay? So we need some source of energy to make that occur. For us, we actually use the chemical energy latent in the compounds produced by photosynthetic plants, okay? So we eat the plants, or we eat things that eat the plants, we get these sugars, and when we break them apart, that gives us a source of energy. The primary producers, the photosynthesizers, their energy essentially comes from solar photons that they have evolved to be able to exploit. Okay, so this is how a very simplified view of life looks. But this is now our template. So it seems like we're being absurdly reductionist, okay, but we've now said that we want to look for places in the solar system, in, well, we can't say the universe, that, let's say places in that little red ring where there's, well, let's be more specific, liquid water, molecules containing carbon atoms, and some source of energy to make stuff happen. That's really our very basic plan. Now, I wrote this talk, I wrote this talk maybe about 2 years ago, and I contrasted our recipe for basic life with our recipe for advanced life, basically coffee, internet access, and your iPhone. And I don't know, is it prescient that these are the 3 things that are basically keeping us going right now in a very alternative living style? But anyway, I'll muse on that later. Now, where are we going with this? Okay. Well, we're going to go out into the solar system. In this particular talk, this is going to be the location in which we're going to look for life, right? There are many other places you might look at, exoplanet systems, this kind of thing, but we're going to focus on the solar system in this talk. This is our map of the solar system. So essentially, what have we got? We've got the sun in roughly the middle. Now, I should say as well, nothing is to scale on this map. Okay, it shows the right relative locations of everything, but the distances between them, the scales, everything, right? There's no information there. This just helps us give a visual association of where we're going to be looking. And so on the right-hand side of the diagram, we've got the inner or terrestrial planets. So you've got Mercury, Venus, Earth with its moon, and then Mars. Then you've got the asteroid belt going around them, and then on the top left of the plot you've got the gas giants or the Jovian planets, Jupiter, Saturn, Uranus, Neptune. And I do like this plot because there's Pluto peeking in at the very edge, basically saying, me, I could still be a planet. Okay, so where we're going to go to in this particular talk, we're going to spend part of the talk talking about Mars and the possibilities for life on Mars, and we're also going to talk partly about the possibility of life, well, not on the Jovian planets, but let me show you the next slide. This is a very interesting representation. We're going to talk about the possibility for life on the moons of the Jovian planets, okay? So at the top here, you can basically see moons of the solar system with a correct scale to Earth's moon and Earth arranged in order of where they are. So you've got basically, starting on the left, you've got Earth's satellite, the moon, you've got Mars with Phobos and Deimos, there's a couple of small moonlets around asteroids in the asteroid belt. But then when you get to the Jovian planets, Jupiter, Saturn, Uranus, Neptune, the moons become planet-sized worlds in their own right, okay? And without enthusing too much about all the variety in these locations, we're going to talk about Europa, which is the second one down from the top of the moons of Jupiter, and Enceladus, which is the second one down from the top of Saturn. And the reason why we're going to focus on these places, well, a lot of you have taught Astro 101, 102, given basic introductory talks. We now know that essentially, well, let's focus on Europa in particular. Underneath that ice sheet on Europa is 2 times the volume of liquid water, okay, I just said liquid water, that exists on that big blue marble-like thing called planet Earth in the bottom right. Okay, so there is twice as much liquid water on Europa as there is on Earth. Okay, the pinky orangey brown stuff that spatters across the front of Europa, we think are basically complex carbon-bearing compounds. Okay, that are possibly upwelling through this ice sheet. Okay, so we've got water, we've got carbon compounds, and we also have an interesting source of energy on all of these inner moons of the large Jovian planets, which is tidal heating. So basically gravitational compression and relaxation of the entire moon as it orbits its parent planet produces internal heat. So we've actually got all of the components for life on these locations. The challenge is getting there and looking for it. All right. I also don't have a watch on and I can't see my clock on my computer, so I'm just going to press on with appropriate tea breaks. So let's go to the first of those locations. Okay. Well, at least go virtually. Okay, so here is our virtual exploration tool. Here's the Curiosity probe on Mars, the rover on Mars, and that's a real physical science instrument, exploration instrument on Mars right now, and it allows us to explore virtually. The quality of the cameras, the quality of the images, why I'm showing you this image is because, you know, the scale on this particular screen really doesn't do justice to this. Is I think about a 3000 by 4000 pixel image. You can zoom right in and see every grain of dust, dent and ding on this Explorer. Okay, it shows exploration in a daily, very practical way. Okay, and given overcoming the latency in communications, it's not instant communications with the rover, but it really gives us a sense of being there and exploring. Okay, now let me show you this next video. To give you the context of this video, I want to give you kind of a movie-like idea of what it's like to explore Mars with a rover. Now, we don't take movies with the rover, okay? We take single images, but what I'm going to show you is a set of images taken by the forward navigation camera that looks out from the front of the chassis of the rover. And every time they need to make a decision about where they're going to drive the rover, they take an image and that helps them assess where they can safely drive the rover. So we're going to stitch all of those images into a time-lapse movie of exploring Mars. So let's go. All right, we checked out that sand dune. We're going to go for a drive. Okay, let's start driving. Checking out various rocks, exploring over the surface. Now, what we've learned by looking at these rocks is that the surface of Mars is pretty uniform. Well, it's all older than about 2 billion years. So the major planetary surfacing, volcanic resurfacing, all happened about 2 billion years ago or longer. Okay, now that's important because what I'm going to talk about in a moment is terrestrial analogues of how we might explore Mars and also what we might expect to find there. So I'm not going to keep talking over the video because the video goes on for about 4 minutes, okay, doing largely the same thing every day. But essentially, we have this old, dry, dusty surface that, well, let's ask the question in a different way because this is how NASA's asking it at the moment. Right, the opportunities for finding life on Mars today are limited, but they may exist, but they're in places that are too difficult for the rover to get to. But what about looking at evidence for life on Mars as it was in the past, so fossil evidence? Because when we look at the geology of Mars, those 2 billion year old rocks, 3 billion year old rocks, 4 billion year old rocks all tell us that Mars was warmer and wetter in the past. It had large bodies of stable liquid water. It must have had an atmosphere to help retain those large bodies of stable liquid water. And so basically, we talk about what Mars's warm, wet, early phase. We actually call it the Noachian period, the era of Noah, okay, because of the great floods on Mars. So Mars was warm, wet, and water rich 3 to 4 billion years ago at exactly the same time when Earth was warm, wet, and water rich. Okay. Now on Earth, we know from fossil evidence that life arose in that period, or perhaps slightly preceding it. Okay. That's basically when we have our earliest evidence of life on Earth. And so what are the prospects then for analyzing these rocks on Mars, not at random, but site specifically chosen, and finding similar fossil evidence? That's a very strong part of NASA's thinking. So now we reach the second kind of, thread of the talk. I can't go to Mars, right? Probably in your lifetime, you may or may not get to go to Mars. Okay, so what's the next best thing to going to Mars? Okay, well, the next best thing to going to Mars, if we can go here, is going to Western Australia. Okay, and in particular, this little region of Western Australia that's highlighted in red here, that is very, very old. Basically, it's a region of Australia that is anywhere between 2 to 3.5 billion years old. All of the rocks that show above the surface there and can be studied. So this is essentially going to be my poor man's version of my Martian analog. I'm going to go to a location on Earth that preserves that ancient history and see what we can learn from going there. So I guess in true Indiana Jones style, let's make our way there. Let's fly the, 13 or 14 hours from Vancouver to Sydney. Let's have a quick cup of tea and then go the extra 5 hours to Perth. Thankfully, that's where we were staying. This must have been about 3 years ago we were there on part of an extended visit. And when I realized that I could actually visit this area, well, I decided to go up to this area for a couple of days by myself with the GPS and, well, my walking boots and a big sun hat. Okay. Now, when you get there, let's zoom in and see what that region of Australia looks like. Okay. Well, I basically flew into this area in the top left called Port Hedland, and there, it's an interesting town to go visit. Basically, partly because of all the ancient rocks here, this is a massive iron ore mining area. That's the main industry in this area, and all of that iron ore goes out of Port Hedland. It's really a one industry town. And so when you'll see the car I rented in a moment. It was the smallest car they had to rent at Hertz. But basically, you rent your car, you get in Port Hedland, and you drive 300 kilometers or so to Marble Bar in the interior. And essentially, on that drive as well, you get to see some amazing geological sites. And then there's something very particular waiting for us just outside Marble Bar. So I know we're all under lockdown, and so this is one reason why I thought it'd be good to do this talk, because we get to do a little bit of virtual traveling. So this is a typical day on the road between Port Hedland and Marble Bar. Okay, thankfully this bit's paved. We're going to go off-road a little bit later, but there are mountains, but they are ground down flat after billions of years of erosion. And essentially, what makes this landscape so interesting is any rock that pokes up above this surface is basically 2 billion years old or older. And so it's a geological museum you can travel through and learn from. This is pretty much the only other traffic you see on the road. This is a road train. This is how they get the iron ore from the mining sites to Port Hedland, basically in these quadruple articulated lorries that go about 120 kilometers an hour down these roads. Overtaking them is fun. Let me just say that, especially when it's not a paved road, when it's a dirt road. This is the car I rented. If any of you have seen my car, this little Suzuki area, will know this is basically a souped-up armored personnel carrier. This thing was huge. It did make traveling around really easy. A couple of things, you think I'd have thought about this beforehand, but basically I'm going to visit a whole series of locations on this road, and so I'd mark them with GPS coordinates beforehand, and I'd put in, I think, a 200-meter proximity warning. So when I was within 200 meters of each of these GPS coordinates, I'd get a little ping on my GPS unit to tell me to stop and slow down. I didn't quite do the maths before I left, and when you're traveling at 120 kilometers an hour, that's 2 kilometers a minute. That's a kilometer every 30 seconds. That's 200 meters every 6 seconds. So basically, when my proximity beep would go off, I'd have 6 seconds to decelerate from 120 to 0 and find the individual rock or outcrop I was looking for. I wasn't looking for whole mountains, I was looking for just individual rocks here. You can go and see. Anyway, that's what exploring looks like. Here's a couple of sites that you see on the road, okay? It really was, there was one turn to the right, I think, in 300 kilometers. That was the only navigation I had to do. You see emu and kangaroos out there. In the top right, that's a termite nest, okay? Remember I told you a lot of these landscapes are very flat and highly eroded. And so these termite nests that are about 6, 8 feet high here, they're really notable on the horizon, especially when you go through a colony of them. And then bottom right, that's my destination, Marble Bar, Australia's hottest town. And it gets to about, I guess, about 50 degrees Celsius in the shade in the middle of summer. Thankfully, I was there in July, so the middle of their winter. Pardon me. So when I arrived there, in the end of a nice sunny day in July, it was only about 35 degrees in the shade, Celsius. Okay. And this is just a quick close-up. The geology is wonderful if you're a geology geek like me. This is the Marble Bar, right? So basically Marble Bar is so called because there's a big lump of marble that juts across the river there and basically creates a small waterfall. And this is what the bar actually looks like when you get close to it. This is with it dry. If you actually take your water bottle and spend a little bit of your precious water to wet it, you get these amazing colors coming out. It's an incredible formation. Now, before I show you this panorama, this is basically the next day. So I spent the night in the roadhouse at Marble Bar. The next day I got up and I had my GPS coordinates of a single rock I was trying to find in this landscape. And I mean a rock that's basically 2 feet by 3 feet wide. So that was my challenge for the morning, was to find that. And thankfully somebody had given me the GPS coordinate for it. So I drove out of Marble Bar on the dirt road. Then I had to go off-road for a few kilometers before I reached the site where I could park the car and then explore for about 500 meters on foot to try and find this rock. So here we go. This is where I parked, and this is what we can see. So this is actually a panorama of what you see when you get a car. There's a little bit of a soundtrack of wind blowing as well. It's pretty quiet here. All of those low beige mounds in the foreground, that's spinifex grass, which is basically, just think of it as armor-piercing grass. And then a few trees. You can just see the car park down there where I've left it. What that means is that's a flat piece of gravel about 2 meters by 4 meters where you can actually leave a car. And then I went exploring over the hillside, and then surprisingly, and very surprising to me, I found this. This is the rock I was looking for that told me I was in the right place. Okay, and you may think it's just a rock, but to the trained eye, you can see all of these wavy features in here. And once I found this rock, I knew I was on the right track. And so I was then able to go and explore and find more features like this. There's my hand for scale. What you're seeing here, this is the earliest evidence of the earliest large-scale fossil evidence of life on Earth. And it's about this rock, about 3.5 billion years old. And what you're seeing there, well, the best way to imagine this is imagine taking an egg carton and turning it upside down, and then that feature is then mineralized in the rock, and the rock is then eroding down from the top, exposing those cones of material. These are basically the features left by colonies of bacteria, photosynthetic bacteria that were growing in a salty ocean water lagoon about 3.5 billion years ago. These were growing a few feet high, and they were basically on a limestone shelf. Okay. Now this is 3.5 billion years ago. This is during Earth has had a long warm wet phase lasting billions of years. Mars didn't have a long warm wet phase, but it did have a warm wet phase at the same time. So what you really think of when you go to a site like this is, are there features like this waiting for us on Mars? Now you might look at those features and say, how can I be so sure that I'm looking at colonies of bacteria growing in a shallow saltwater lagoon? Okay, well, because interestingly, a few hundred kilometers away is the real thing still happening today. Okay, this is Shark Bay This is just a little bit further down the coast from Port Headland. And what you have here is, well, you can't see the limestone reef because all of these black mounds are on top of it. And all of these little black pedestals, those are mineral features created by these photosynthetic bacteria, these stromatolites. Okay. Now, what they do essentially is they grow in a mat, and bacterial mats are very well known. But what the bacteria do is they produce a slimy mucus that traps sand and then sets into kind of a bioconcrete material that then builds up layer by layer with time. And if you actually cut through one of these stromatolites, you see exactly that finely layered structure that we saw in fossils as well. And that's where the name comes from. Stroma, the stroma are basically the layers that you see in the rock. And though it looks like the ocean out there, well, actually, you're at the very far end of a large lagoon, right? Basically about 60 or 70 kilometers long. And so the entrance to the ocean is about 60 kilometers away from here. But this lagoon is only moderately cycled by the tides. And so evaporation has created this sort of hypersaline environment, which is good for the bacteria because otherwise they'd be grazed upon by small shrimp. They can't survive in the high salinity environment. So this is our idea. Is this what Mars looked like 3.5 billion years ago? Now that's speculation, but speculation's fine as long as it pushes you to explore. And so really, this was my poor man's way of doing this. So let's watch this short video because the place that NASA's next rover, Mars 2020, or it will be known as Perseverance, is going to a place called Jezero Crater, but the feature it's going to explore there, the primary feature, is essentially a 3 billion year old or so delta, river delta, essentially. So let's just take a look at that.
This flyover was produced from NASA images taken from orbit. The blue circle indicates the area the rover will likely land. The arcing hills in the center, 1,600 feet high, and are the rim of Jezero Crater. The central goal of Mars 2020 is to learn whether life ever existed on Mars. It's too cold and dry for life to exist on the Martian surface today. But after Jezero Crater formed billions of years ago, water filled it to form a deep lake, about the same size as Lake Tahoe. Eventually, as Mars climate changed, Lake Jezero dried up, and surface water disappeared from the planet. An ancient lake is a fantastic place to pursue our goal of looking for possible Martian life. On Earth, lakes are filled with living creatures. Evidence of that life is often preserved in the mud and sand deposited on the bottom of the lake. So, we use the rover's instruments to explore the rocks of the ancient lake bed. Here we can see evidence of the former lake. The canyon cutting through the crater rim was carved by Earth. As the water entered the lake, it slowed and dropped the sand and mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years, called the prime mission. During this period, we used the rover science instruments to analyze the lake sediments. After we explore the delta, we hope to investigate the shoreline of the former lake. To get there, we have to traverse around a sea of modern sand dunes. From this perspective, you can see former shorelines curving around a headland. We can picture waves in Lake Jezero beating on a sandy beach. And finally, we will press on to the crater rim. Jezero Crater when a large object collided with Mars, excavating rocks from deep in the Martian crust, exposing them in the rim for us to study. These rocks would have been hot shortly after the impact and may have hosted hot springs. Deposits from these springs would be another target in our search for possible ancient life on Mars.
All right, so hopefully that's formed a link for you between why I went to Western Australia hoping to learn about what Mars 2020 might learn about in Jezero Crater. Okay, now I'm just going to skip out the presentation for a moment. How am I doing? That's better than I thought, 12:33. Okay, because that was the first of the topics I wanted to talk to you about. So the second of the topics, where are we going to go now? All right, going to go back to our map. Well, now we're going to go skip from Mars to our second location I told you would be interesting, not the Jovian planets themselves, but the moons of the Jovian planets. And in particular, okay, we're going to focus, actually, well, we're going to focus on, I'm going to show you some internal structure diagrams for Europa, but you know, we could be having the same conversation about tiny Enceladus as well. Okay, so let me just, that reminded us that, you know, is a move of Jupiter. So let's take a close-up image from the Galileo space probe. Okay, here you can see, well, the white stuff we know is solid water. Okay, we know that for sure because we can see the spectroscopic signature of sunlight reflecting off it. Okay, the pinky orangey brown stuff we know as pinky orangey brown stuff. Okay, that's because its absorption signature in sunlight is essentially, well, it's exactly what we'd expect for a whole load of different carbon-bearing compounds with many absorptions that are basically overlapping with each other to create an unrecognizable sort of blend. Okay, so when we talk about pinky orangey brown stuff, it's basically accumulated, I don't want to, if I use the word organic matter, I'm using it in the chemical sense where you're talking about sources of reduced carbon. Okay, so carbon bearing compounds that could be broken apart and oxidized further. Okay, but beyond that, we really don't know what the pinky orangey brown stuff is. Now, what's great about Galileo is, I'm not going to go into detail about the measurements, but we know a lot about the internal structure of Europa. Okay, and that internal structure is, well, let's think about the overall size of the moon. So what have we got? We've got a radius of about 1,500 kilometers or so. Okay, so a little bit smaller than our moon, but you know, ballpark. Okay, the first 10 to 30 kilometers of the surface are probably that ice crust. Okay, now we've learned from looking at ice crusts on Earth that they are anything but static entities. Flow, they warp, they convex. Lots of interesting things, lots of things happening in that ice crust. Underneath the ice crust, we know there is about 100 kilometers of salty liquid water. Okay, we know that because we can see and measure the magnetic field that is in that conducting medium by Jupiter's vast magnetic field. Okay, underneath that, and this is an important point, directly underneath the liquid water is rock. Okay, and that rock goes down for a large fraction of the radius of Europa, and then you have an iron core, a solid iron core in the center of Europa. If it was liquid iron, then that would be great. That would be a nice conductive medium, but solid iron is much less conductive. Okay, now this is important though, because think of what we have here. You have rock in contact with the water, and not just rock in contact with the water, warm, hot rock in contact with that water. It's that rock is heated by the daily, or well, the orbit of Europa is, I forget the exact number, it's about 7 days or so it takes to go around Jupiter. So every 7 days, Europa is squashed and squeezed by the gravitational field of Jupiter. And just like if you squash and squeeze a squash ball or a racquetball ball, you will dump heat in there, frictional heat. And so the interior is heated by frictional heating, whose ultimate source is tidal interaction with Jupiter. Now that hot rock is in contact with water. Okay, now that system is exactly the same system we have on Earth, where we have an ocean in contact with hot rock. Okay, and so as an astrobiologist, if you wanted to know, well, what kind of habitats might you get on Europa where you have hot rock in contact with water? Well, what I'm telling you is that the similarity of that system to Earth means you can go to places on Earth where you see hot rock in contact with seawater, and that might tell you what to expect, might being the operative word here. Okay. Interestingly as well, now I don't know if you caught that, I said that ocean is about 100 kilometers deep on Europa, and you might think, well, that's incredible. If we ever went there, wouldn't any probe be crushed by the pressure? And it's one of those neat conspiracies of physical properties that although the water is 10 times deeper than it is in any ocean on Earth, the gravitational field on Europa is approximately 10 times less than on Earth. And so the weight of that water, even if you're at the bottom of that 100-kilometer ocean, the pressure is going to be the same as it would be at the bottom of the Mariana Trench, the Challenger Deep, which is about 10 kilometers deep. So actually, there is a great many physical similarities between Europa's ocean and Earth's oceans. Okay, so that was my motivation for seeing, well, where can I go and actually see that hot rock water interface, and what does that do for biology? I thought I'd go further than Vancouver Island in my search, but it turns out that just off the coast of Vancouver Island, we actually have really the poster child for hot rock interactions with seawater, and basically some amazing biology and physical chemistry that happens. So what have we got here? So here's a map of Vancouver Island, and I haven't got a pointer, but hopefully you all know enough about Vancouver Island to recognize where Victoria is, basically at the bottom right of that diagonal island there. And then you can just see the Olympic Peninsula of Washington just south of us, and then the Strait of Juan de Fuca. And once you go out of the Strait of Juan de Fuca, you're basically in the Pacific Ocean. Now, what makes this place interesting as a scientist is this whole location. You essentially have the Pacific plate is hitting the Juan de Fuca plate and is basically being pushed underneath it. And essentially the whole thing is then being, sorry, yes, I am being right here. Basically the Pacific plate is being pushed under the Juan de Fuca plate, and the whole thing is basically subducting under the North American plate. So you have a massive subduction zone where basically one oceanic plate is going underneath the continental plate. And where that really generates some interesting stuff going on is you can just see, let me see if I can describe it to you. So go to the sort of middle left of the image and down until you see that little orange square that says Endeavour, okay? That's where we're basically seeing a lot of the heat generated and released by the subduction process, okay? And so Endeavour is where we're actually going to go to. Now, how are we going to get there? Well, we're going to have to go in a ship, and that ship is the Nautilus, a research ship I was fortunate enough to be invited on. And let me just give you a quick tour of what it's like to be on a research ship. So this is a great video tour where you see the Nautilus, and in the bottom you can see the yellow dot moving around the ship, and our actual view of the, in this case, here's the main deck where the fancy cabins are. There's the mess room next to the galley. That's where we have all of our meals. There's a lounge there where you can hang out when you're not on watch. Go out the back of the mess. There's the sun deck where you can eat your meals in nice weather. And then here we go down to the operations deck. This is where all the action happens. This is where the two remotely operated vehicles, or ROVs, are kept. There's Hercules and its hangar. It's an experimental ROV. Every ROV effectively is. And so it has its own workshop, basically, to keep it operating. It operates down to about 4 kilometers ocean depth. And so after any dive, there's a lot of basically maintenance and checks to be done. Now we're heading on one of the lower decks. Here's the data lab, as well as the ROVs. There's a state-of-the-art sonar array underneath the ship, and that allows us to do multi-beam seafloor mapping. All of that gets processed in here. These two guys are going to show us lots and lots of computers. They've been told to put on their crew shirts and wave, here are the computers, lots of servers, okay? Partly that's also because in addition to the multi-beam sonar data, all the video data we take under the ocean is broadcast on 3 HD channels to the world, right? And that's a lot of data. This is, you won't believe it, this is the TV studio. This is where we do a lot of live broadcasts to museums and schools. Once a day, I try and get to the gym, rather like we do at the moment. I'd find 10 minutes of exercise would keep me going every day. Here's the wet lab, where any samples that the ROVs return to the surface are then processed. And then where are we going to go now? Let's just go up to the, there's an observation deck where you get a great view of how the ROVs are launched. I'm going to show you a video of that in just a moment. And then this is important now. These two shipping containers that have been welded together, this is the control room. And I'm going to show you another video that shows the control room in operation. But this is essentially where we operate the ROVs from, and where the scientists who are trying to interpret what the ROVs are looking at get to interact with the pilots who control them. So this is, if you like, this is mission control on board the ship. Just a quick visit to the bridge. I don't normally get to spend much time here. Yep, the ocean's still there. Good, he's checked that. All right, out from the bridge, and then let's do one last trip up to the top observation deck. And this is a great spot for really just hanging out at the end of a sunny day. All right, so that's the Nautilus, okay? That was where I was essentially based for 3 weeks in, let me see, was the first one 2017? The first trip I did on the Nautilus. Now, where are we going to go next? Well, this is just another video, where this is just a slower video now, where we can see inside the control room. And this is essentially the nerve center, as I said. So imagine two rows of seats and controls. And actually, for those of you who've been to a telescope, this was really familiar for me in terms of it felt just like going into a telescope control room. Okay. Now, what the rovers see with their state-of-the-art cameras is coming straight through on those big widescreen monitors. Okay. In this case, they're actually looking at a World War II submarine wreck. Okay. But really, this is designed to give the pilots as much of a virtual feel for operating underwater as possible, because as soon as they move a joystick, there's no latency in the command. They're basically moving the ROV in real time. So as much as possible, you need to give them the same spatial awareness that a pilot would have actually in that ROV. Okay, and so the way they achieve that is quite incredible, right? That you really do get the sense that you're actually down there. There's two big monitors because there's two ROVs, Hercules and Argus, that work as a pair. And then, rather like a telescope as well, you've got a huge load of ancillary screens that basically give you telemetry that might be useful at some point in the dive, i.e. what the electrical systems are doing, what the biological systems are doing, what the remote controlled arms are doing as well. Okay. Now I'm actually hidden off to the far left in one corner of that front row. That's where my seat is a science communication fellow. And my job is basically to take these images and also the conversation you can hear of all the scientists that goes out with the video feed, and basically help everybody in the room be aware of you guys, the audience, to make sure that our conversation is always reflecting what might be things you're interested in, that we're always speaking in plain language. And also, just like this Blackboard session, I have a chat feed where I can see questions and comments that people post to me from all the way around the world. And when things are nice and quiet, I actually build those into the conversation. So that video is done. Let's just take one more sort of close look now. This is a close-up look of ROV Hercules. You can see it's essentially manipulator arms on the front. You can see some of the cameras, but there's basically about 15 cameras all the way around, pardon me, all the way around Hercules. The main one in front, well, that takes the, full HD images. These are the ones that we sell to Blue Planet and companies like that. It's basically a chassis, and then on top of it, all of that yellow stuff, that's syntactic foam. That means foam that basically won't compress under pressure. And that's what gives this, essentially, it's about the 6,000, sorry, let me see if I can get this right. It's basic, yeah, it's about a 6,000 pound piece of technical equipment here that as soon as you put in water is slightly positively buoyant. Okay, it's slightly positively buoyant because in case the power gets broken when you're exploring at depth, then the ROV will eventually float back to the surface. Okay, and so then what you do is actually get down to the ocean floor. You use those thrusters to actually push the ROV down to the ocean floor. Okay. There's Argus, which is the teammate, if you like, that operates always kind of above and behind Hercules. It's like the eye in the sky that shows the pilot where Hercules is operating on the seafloor. That bucket you can see on the front, that's basically the improvised lens cap for its own HD camera. And then let me just show you one video that shows how we actually get those ROVs into the water. It's a really professional operation. So Hercules comes out of its hangar and we attach a crane to it. The pilots are all in the control room at the moment, ready to go live. They don't have control of the ROV at the moment. We lift it up, nice calm sea, put it in, detach the cable, and then the pilots are able to move Hercules to the stern of the ship, waiting for Argus to be launched. Argus is launched, and you can see that cable going to Argus. That's a 6-kilometer long cable. Okay, so that's what's allowing us to basically then tether these operations all the way down on the seafloor. So that's really the exploration technology. Why are we going to Endeavour? Sorry, that's just a little graphic here. Those are the two working as a tandem team. Why are we going to Endeavour? Well, what was the last thing I told you about Europa? Well, Europa, we have hot rock in contact with the ocean water of Europa. Now, on Earth, it actually took us quite a long time to realize that the heat we know is inside planet Earth doesn't come out uniformly. It comes out in cracks in the surface that are like short circuits for heat flow through the surface of the Earth. And those cracks in the surface of the Earth we now call tectonic plate boundaries. And this is a map of tectonic plate boundaries on the globe of the Earth. And you can also see, marked in this colored dots here, are sources of geological activity, whether that be earthquakes, mid-ocean ridges, volcanoes, all the things like this are associated with this tectonic activity, but they're all pretty much concentrated on these cracks. And so what we've learned on planet Earth is that the heat doesn't come out on average, it comes out through these cracks in the surface. And so Endeavour off Vancouver Island is basically up there in the middle top right at the Juan de Fuca Ridge. That's where we're going to go with Nautilus to try and explore what happens when you go to these locations. Here's kind of a schematic of what we're going to expect when we see there. So essentially what you've got on the right-hand diagram is that crack in the surface. That dip between those two mountains is that mid-ocean ridge. All that happens at Endeavour is that mid-ocean ridge, because of the plate boundary, is not in the middle of the ocean. It's about 250 kilometers off the coast of Vancouver Island, which makes it relatively easy to get to. So the crust is pulling apart here. You've got those purple arrows showing the spreading axis, and basically weakens the surface of the crust there and allows that magma below to get much closer to the surface than it normally would, within a few hundred meters of the surface. Now, the floor of the ocean is porous, and so what you see is those blue conduits of seawater is water that's percolating down through the ooze and the rock. It comes into contact with the hot rocks near the magma, and just like at Yellowstone National Park, hot water that's heated by those rocks is more buoyant than the cold water, and it rises up through that spreading axis to the surface. Now, what also happens there is you haven't just got hot water, you've got water that's been heated in contact with rocks. And basically, many, many different types of minerals get dissolved in that hot water. So that water is coming up at about 350 degrees Celsius or so at this particular location. As soon as it comes out of those cracks in the Earth's floor, it hits seawater at an ambient temperature of 2 degrees Celsius. So it cools down very rapidly, and all of those minerals on board are going to precipitate. And it looks like clouds of black smoke at this particular location, which is why these hot water springs here are called black smokers. Now, what the original explorers of mid-ocean ridges didn't expect to see was so much biology there. And really what we're going to see when we see these videos of Nautilus exploring and Hercules exploring these mid-ocean ridges at Endeavour is going to be abundant biology. And all of that biology is powered by microbes, chemosynthetic microbes, that basically use the electrical energy held in those dissolved minerals as the source of their metabolism. Okay. Now, this is very important because we're always trying to use this as an analog for Europa. Okay, so we have no sunlight down here. We have geochemical energy as the basis of the food chain. And all we're seeing that geochemical energy is coming from is seawater in contact with hot rock, exactly what we think might be going on Europa. So now let's actually go there. You've now seen the technology, you've seen where we're going to go. So here is a video of Hercules exploring the Endeavour mid-ocean ridge, and this is what you see when you go there.
See that these giant sulfide towers that are formed by the precipitation of minerals from these hydrothermal vent systems create a real navigational challenge on the seafloor.
And temperatures right at that vent for the guys tuning in can reach 600 degrees Fahrenheit, so it's very hot.
As it comes into contact with the cold seawater, the mineral load carried dissolved or partly dissolved in those fluids is very rapidly precipitated. Those minerals have a very dark color, black color, primarily iron sulfide with perhaps some copper and zinc sulfide in there.
The clock is on. Okay, so let's see what happens here.
I feel like I'm actually warming up physically.
Yeah,
Like,
I just take our jackets off here.
Sweating.
We got through 24.1. Will it get any higher? 324.2. 3.
Oh! 226!
Can you believe it, folks? I can't believe it.
I can't believe what I am seeing.
That smaller little chimney to the left of the lasers, that might be some sulfide worm colonies, more active hotter area. Seeing scale worm over on the right side, that white scaly worm.
Just don't knock it over, Bob.
Looks pretty sturdy.
Yeah. Just don't knock it over, Bob.
So yeah, you can see some palm worms in the shimmy water, Regia,
There we go.
the bright kind of foamy or hairy looking brush-like blooms. It's kind of a textbook, beautiful view of diffuse flow and some focused flow. Yeah, there's some sulfide worms there. You're seeing lots and lots of lipids. It's probably a lot
On top of
cooler
chimneys, right? Yeah.
behind
No, I
that
think it's perfect.
triangle. You've got some pretty healthy looking regia.
Look at the shiny pyrite.
And then as the A team's done here, we'll have somebody else come in and recover for us.
Yep. Is that the ROV equivalent of a mic drop?
Not really. We dropped enough stuff.
All right, so I guess the question then is that a valid expectation of the environments on Europa might look like? Here's kind of a NASA old school artist's impression of Europan hydrothermal vents. And well, I guess kind of, that is speculation, okay, but it's the right kind of speculation in that it helps us inform future space missions and tells us how we might design them and what kind of things we might look for when we go there. I mean, the next thing we really got coming up to Europa, a specific Europa mission, is Europa Clipper. Now, as you know, we rarely throw the ball long anymore. Europa Clipper is basically asking some pretty important but incremental questions. How thick is the ice sheet? Okay, does it? Can we see evidence of ice dynamics? How deep is the ocean that we see from the magnetometer data? This kind of thing. So we're still trying to learn a lot about the environment, but stay tuned. And that basically brings the talk to a conclusion. Hopefully you've enjoyed those two adventures that taught me a lot of astrobiology, and hopefully a bit of astrobiology for you as well. So thank you very much.
Thank you, John. I think there is an applause option. Jacqueline is the innovator of the group. I think we're all giving you our virtual applause, even though I don't dare unmute everybody to hear it. And I think we'd like to open the floor to questions. Does anyone have any questions for John? Nika left some feedback, which I will address post-session. Did we have anything else in the chat? Well, I have a question to start. So all of these investigations, well, actually, we have one from Falk. Falk, do you want to pose your question? Feel free to unmute yourself.
I was just wondering, you mentioned these lines on Europa on the surface, and you could see them. You could give them a name. I didn't hear what the name was. Is it known where these lines on top of Europa come from? Are these features, these patterns?
Well, they're given the really wonderful name linnae, which I guess anybody with their Latin knows just means lines, right? What we speculate is that these are essentially, think of it as ice tectonics.
All right, we have a question from Logan.
Hi, John. Yeah, I was curious about those stromatolites. So the layering that you see in those, what actually produces the distinct rings that you see in those? Is that from seasonal variations, like you might see in rings on a tree, like repeated growth and die-off of the bacteria, or something else?
Oh, that's a great question. So if you were to actually take a cross-section, right, you'd see what it almost looks like taking a cross-section of a cauliflower, right? And there, each of the individual layers in the cross-section would be associated with different generations of bacteria that basically, once one layer of bacteria forms a layer and mineralizes the hard surface, then, well, eventually less sunlight is getting down to the lower level. So it's like condos. You've got to build up and up and up all the time. So those are growth rings. But essentially those ring-like features you saw in where I had my hand. So imagine the bacterial mat, those stromatolites, imagine they look more like an upturned egg carton, okay? And then imagine doing your cross-section coming down layers through that egg carton. So you're almost like taking conic sections. So in a sense, they are growth rings, but the geometry is a little bit different, in terms of how they're being exposed. Does that answer your question?
Yeah, thanks.
We have one from Ariane. If you want to unmute yourself.
Yeah, excuse me. Forgot to click on the micro. I was just wondering how similar we can expect the hot thermal vent on Earth to be from the floor of Europa, because we're talking about something that is like very hot coming into contact with cold water. But if I how hot would be the rock mantle of Europa? Because if I understand it well, it's not this kind of viscous pasta that is the earth magma. It's more like rock, so it might not be that much of a big difference.
No, that's right. And we do see vents on Earth as well, in Earth's oceans, that go down to as low as 40, 50, 60 degrees Celsius. So we do see different temperature ranges in the vents we see on Earth. And also, if you believe that the European vents, even if they existed, were going to be exactly the same as planet Earth, that's probably naive. Okay, at least what you should take from this talk is that there's enough potential similarities of hot or warm rock in contact with ocean water that it tells us that looking for vent-like features or areas of focused flow, if we do identify them, that is where the biology may well be.
Another thing I was wondering also is about the hot thermal springs. You briefly mentioned that in when you showed the Mars 2020 video, and I'm wondering if this is another place you can. I mean, you can look for another for Earth analog for hot spring on the ground, like Yellowstone or wherever. So I was wondering if this is another place you may look at for on Mars. If are hot spring likely to be common? Because for what I know, I think the geology of Mars in terms of volcano is slightly different than from Earth.
No, that's another good question, and the answer is yes. So they did mention that briefly in the video, that there are certain rock types that have been identified on Mars that are similar to rock types on Earth that indicate they were laid down as basically precipitation on a real hot spring, not an oceanic hot spring. And we don't know where life started on Earth, and so we speculate. Some people speculate it started at deep ocean hydrothermal vents. Some people do speculate that it started at terrestrial vents, more like the Yellowstone kind of environment, and we just don't know. And so the idea is that Mars 2020, it will have the ability to recognize those rocks when it finds them, and so finding them and studying samples from those areas is part of the mission.
Okay.
Nick, why don't you go ahead?
Yes, hello. This is perhaps less an astrobiology question and more a planetary science question. Maybe I missed it, but what exactly is measured in order to estimate the internal composition of Europa, for example? Like you mentioned you had the chart earlier. We know the core is solid iron, for example. We have estimates of the depth of the ocean. How exactly is that measured to get?
That's a great question. I don't go into it in detail in the talk because it's a bit of a technical diversion, but essentially it's two sources, right? One source is spacecraft Doppler telemetry. Okay, so essentially, as the spacecraft executes a flyby of a moon like Europa, its trajectory changes, and its trajectory, well, at a low level of understanding, you would say, okay, it responds to the mass of Europa. But we know as well, it doesn't just respond to the mass of Europa, it responds to the mass distribution of Europa. So the spacecraft would execute a different trajectory if Europa had a uniform density, as opposed to if it had a differentiated density profile, say a dense iron core and a rocky mantle-like feature. And that's what we see. We can see from the rate of acceleration and deceleration of the probe as it executes a flyby, it gives you broad brush, not detailed, but broad brush information about the interior density variations of the moon. So that's one, and that's basically what's giving you the iron core versus rocky outer layer, boundary there, right? The second piece of evidence about the ocean, that comes from a different instrument on the Galileo probe, which is essentially its magnetometer. And what we see is that essentially Jupiter's magnetic field induces a magnetic field in Europa. Okay, and so there you've got to go back to first year electricity and magnetism. Okay, and so you can induce a magnetic field in a conductor. Right? So you've got to have a conductive medium. And so what you're actually measuring is the conductivity of Europa. Now, the solid iron and solid rock isn't going to need that kind of conductivity. Okay, you need something else. And so we know that there is ice on the outside of Europa, water ice, but it can't be solid ice. Sorry, it can't be solid water. It needs to be liquid water, because then you can actually have the ions can move around and you can get up to these big convection currents that they can then create that, or are going to be induced by that magnetic field. And what's wonderful is, you know roughly how much water there has to be to generate that conductivity. So that's where the ocean depth comes from. But there is a slight degeneracy there, that also if you had a 100-kilometer deep ocean that was just pure water, that wouldn't be conductive enough, okay? And, the gravity Doppler telemetry stops you from having a bigger ocean, okay? But what you can then do is add a second parameter, which is the salinity of the ocean, okay? And so what you're actually constraining from the measurements of conductivity from the magnetometer data is essentially the combination of the ocean depth and the salinity. And one of the preferred solutions, right, if you look at sort of the chi-squared confidence contours, is a 100-kilometer deep ocean with something that has a salinity very close to that of Earth's ocean, which also makes sense because the salinity in Earth's ocean basically comes from water mineral interactions at that interface that we call the ocean floor.
All right, are there any remaining questions? Okay, Ariana Moore, and then I think we'll have to call it for questions today. We're running a little bit over time, but go ahead.
Okay, yeah, just from the previous question, can you check, is there a way to check if the surface composition of the ice is, how can I say, consistent with the solution inferred from the flyby of the spacecraft?
Well, not for Europa, but there's a great way you can do it on Enceladus, okay, which, though smaller, about 3 times smaller, actually about 6 times smaller than Europa, we think we have the same thing going on. Ice, rock, we're not sure about the iron interior, but there, different moon, different planet, different spacecraft, the Cassini mission, they've actually flown through plumes of material being ejected through cracks on the surface, which we basically think is ocean water venting out through cracks into space. So we've flown Cassini through that. And essentially, well, it's got 2 instruments on board that are useful, the cosmic dust analyzer and the ion and neutral mass spectrometer. They detect water. They also detect sodium chloride, okay, which is basically table salt, right? And so at about the right concentration to give you the salinity that you also measure on Europa. So the idea that you're looking at salty water here has independent confirmation, but just not on the same moon, because Galileo didn't have that kind of instrument. And although we now know there are plumes on Europa, they're much less active than the plumes on Enceladus. But if we take those ice moons as a class of object, then those different observations, point to salty subsurface water reservoirs, liquid water reservoirs, being kind of a common feature.
Okay.
All right. Thanks, John. And thank you, everybody, for attending today. I think we can call this a success of a medium. I hope you'll all join us next week, where Falk Herwig will be talking to us about 3D hydrodynamic simulations. And we're also still looking for more speakers. So if you are interested in giving a seminar, please email myself or Vita. We'll be chairing for this summer. If you have a shorter talk or something prepared for a conference, we're even open to things like posters. This is a chance for you to share what you're doing, and you're allowed to change the format as you might see fit. And beyond that, we'll see you next week. Bye, everybody.